Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3, Section 1. We will present our final project. First, I will introduce myself and my members. Me is MEOR Muhammad AIMANNUDDIN bin MEOR FAIZAL. Matric number CE240019. My second member is Muhammad AKHYAR bin MOKHTARUDDIN SHUBLEE. Matric number DE230071. And my third member is Rasyid bin KASIM. Matric number DE240109. My fourth member is MUKHRIS bin NOORZAN. My matric number is DE230116. And my last member is FLAVIO anak RUTUT. Matric number CE230010. Okay, for our parameters for our group is for F0 is 200 kHz for fundamental frequency. For the T0 is T over F0 for our period in second. For our tau is 0.5 time with T0 for 50% duty cycle. For FC for our group is 700 kHz cut off frequency. For ANAK is 20, and for the harmonic integers is n equal to negative n max. We divide with n max. For the t equal to line space, negative t times with t0, 2 times t0 over 100, 1000 for our time vector. Okay, for Fourier coefficient is Sn 0 size n, I is for I equal to 1 per length, n I equal to 0, Sn I equal to tau per t0, Sn I equal to tau per t0, C pi time ni time tau per t0 per pi not pi time ni time tau per t0. Okay, for our first task is time domain signal approximation. Okay, for the first is xt0 size t, xt10 0 size t, and our third is xt20 0 size t. Okay, I will open our result for easy to explain. Okay, this is our first task is our result graph. Okay, for the xt equal to Sn and time exponent 1j times 2 times ki time ni time t per t0, and absolute ni for accuracy. For the n5 xt5 equal to xt5 plus xt, and for the n10 we can see is xt10 equal to xt10 plus xt, and our n20 is xt20 equal to xt20 plus xt. Okay, for the xt original equal to xt original plus xt for sum all for original. Okay, xt5 real, xt5 for our first graph, and xt10 real xt10 is for n10, and xt20 real xt20 is for our original. Okay, for our table figure name is task 1 time domain approximation. Okay, subplot T11 plot T times Li exponent 6 xt5 for n5 title, and 5 x level. For the x-axis is our time in microsecond, and our y-axis is amplitude. Okay, same goes to N10 and N20. That's all for me. Thank you.
Hello, my name is FLAVIO RUTUT. My metric number is CE 230010. I will demo for frequency domain analysis and task 3 RC low pass filter. Firstly, you need to write the command, which is f equal to n times f0. Then write the main x equal to abs. Then we write command paste equal to angle, which is angle times to 180 pi, and we write the figure name task 2 with frequency domain, then write the subplot 211 and steam f slash 1e3, then main x pellet title, x label frequency kilohertz, then y label magnitude and grade on. Next is same like the before, subplot 212 steam f slash 1e3, then we write paste here and plate title and x label frequency kilohertz, then y label as degree grid on. Next is task 3, which is RC low pass filter. What we need to write the command is hn equal to what slash bracket 1 times 1 plus 1 j times f slash fc bracket, then we write main hash equal to abs, this is sn, then we write pass hash paste hash equal to angle sn times 180 pi, then we write figure name task 3, which is filter response, then we write subplot 211 plot bracket f slash 1e3, then main hash magnitude hash, then write title hash f, then x label frequency kilohertz, then y label magnitude, then we write grid on. Same like before, then we subplot BEJ202 and plot f/1e3. Then we write paste hash here, vector hash ss, then x label frequency kilohertz, then y label test degree breakpoint. So the result for domain analysis and task 3 RC low pass filter is like this. So this is a frequency domain for task 2. Then this is task 3 filter response. This is the graph. That's all for me.
Assalamualaikum warahmatullahi wabarakatuh. My name is MUKHRIS bin NOORZAN and my metric number is BE2030116. Today I would like to present about the task 4, which is the filtered signal. So first of all, for the coding, the filtered x is equal to xn times hn is represent the Fourier transform of the input signal, and the hn is represent the frequency response of the filter, and then it is stand for the equation yf is equal to xf hf, and then the max filter is equal to abs, and the first filter is equal to angle filter dx times 100 over 118 over pi. This is the convert the pace to the degree, which is it make it easier to the interpreted. Next is the plotting for the filter spectrum, which is figure name. This is for the task 4 and the filter spectrum. And then the subplot, we put the value, which is 211. This is the display the magnitude of the filter spectrum. And then for the FIE3, it represent the frequency that we want to convert from hertz to kilohertz. And then STEM is represent the signal in discrete in the frequency. So this the title show the mathematically representation of the filtering signal. And then for the result that we got is the graph explanation at here. So the max is 0.5 and the lower is at the 0. So the peak of the result represent the frequency component that pass through the filter, and then the component outside the filter passband are significantly attenuate or removed. And then the strong peak is around 0 kilohertz at here. And then this is the confirm that the filter is working as intended. So next, for the first spectrum xn times hf, it show the phase of shift introduced by the filter, and then the phase value is between 100 to minus 118. So this phase is information that understanding the signal distortion and the delay. So the abrupt change in phase occur near frequencies where the magnitude is small. So that's all for me. Thank you.
BE2030071. So now I'm going to continue with the simulation of time domain reconstruction after the filter. So as you can see here, This code use a loop to perform Fourier synthesis. So it takes each frequency component and multiplies it by corresponding exponential and then sum it together. So this transforms the signal from the frequency domain back into the time domain to allow us to see the smooth effect that filter had on the square wave. So let me run first. Okay, here are the result of the filter signal in time domain. So if this were an ideal square wave, this line will be vertical and sharp enough. So this show us that the coding is working because of the sharpness of the square wave gone by filter. So here are the result. They are not sharp enough. They are filtered already. Okay, I think that's all from me. Thank you.
Assalamualaikum and hi, my name is Rasyid bin KASIM, number matrix DE2040109. So in my parts, I want to demonstrate or explain the coding of our project for the task 4, that is filter signal. So basically in this section we apply a low pass filter LPF to the Fourier series coefficients of our square wave signal. The goal is to observe how the frequency components are modified when passed through an RC filter. We calculate the filtered spectrum by multiplying the original Fourier coefficients xn with the filter response hn. So filtered equal to xn here, and make filtered equal to abs, and phase filtered equal to angle, that is 180 over pi. We plot the magnitude and phase of the filtered spectrum using stem plots, and the result shows how the LPF attenuates higher frequency harmonics while preserving low frequency components, which is expected because low pass filter allow low frequencies to pass and reject high frequencies. So we run. We wait for the signal. Wait. Not coming out. Alright, it's okay. Okay, we continue. The graph helps us visualize the effect of the RC filter in the frequency domain, and then the next part that I want to explain about the extra compare original versus filtered in frequency domain. So after we inspect the frequency domain, we reconstruct the filtered signal back in the time domain. Then we compare it with the original unfiltered signal. How it's done? We reconstruct the time domain waveform using the filtered Fourier series. Then we compare the filtered signal to the original using time domain plot. Okay, that's all from me. Thank you.